Hello, this is going to be the first in an 11-part video series that goes through a tutorial of how to do the practice problems for the tests, so the tutorial tests for fluid mechanics. That's ENGPHYS 3004 at McMaster University. This is a partner video series to the video series produced last year on the lecture content. So the other video series would be about teaching the material behind it, and this one is extra video practice just for solving practice problems. So for this one, we're looking at test 1 from 2018. This is being recorded after the test is already done, so more for next year or for exam review for this year. Now, the first question: if the dew point in a factory is 10 degrees C, determine the humidity if the current temperature is 20 degrees C. So the first thing we need to know is what the dew point is, and the dew point is the temperature where water is going to start condensing out of the air. So water is going to start to form liquid droplets. It's not going to exist in an evaporated form anymore. If something in the factory gets to this temperature, then there's going to be water appearing on it. So maybe you have a cold pipe. If that pipe is 11 degrees, you're okay. But if it's 10 degrees or lower, you're going to have water condense out of the air in the factory. So telling the dew point, saying what the dew point is in the factory is a way to say what the partial pressure of the water actually is in the air. If we go to our table from the textbook, then you can see that 10 degree temperature for water vapor corresponds to a partial pressure of 1.23 kPa. So Psat at 10 degrees C is equal to 1.23 kPa, I think we said. And the other thing that we're going to need is the saturation pressure at 20 degrees. 20 degrees C is equal to, what was that? 2.34 kilopascals. So the humidity is equal to the pressure is equal to the current partial pressure divided by the saturation pressure. At the temperature that we are actually at. So in this case, it would be equal to Psat at 10 degrees divided by Psat at 20 degrees, or 1.23 divided by 2.34. And let's see. We get about 53%. So that's how you do the calculation of the humidity. All right, number 2, surface treating of silicon can create either a superhydrophilic or superhydrophobic surface. A micromachined silicon tube with an internal diameter of 1 millimeter has been treated to have a contact angle of 0. If this tube is inserted vertically into a pool of water with surface tension of 73 millinewtons per meter, determine how much higher or lower the water level in the tube will be than the water surface. All right, so what we do is, this has to do with the capillary effect, and we have some information on that from our topic summary. So this again is a figure from the book. So this is something we directly talk about. The contact angle less than 90 degrees means that the surface is hydrophilic. We're attracted to that surface if we are water. Whereas contact angle greater than 90 degrees means it's hydrophobic. We'd rather be with more water than that surface. So the capillary rise height is determined directly by this formula, which takes into account the contact angle. It's already really worked out a lot of the math here. And this comes from a balance between the weight of this fluid element that's rising and the force of the surface tension on either of the the perimeter of this contact with this tube. This is for a circular tube. We're looking in cross-section. So what we really need is this formula. This is going to tell us the amount of rise. Amount of rise is this. So this will specify whether it's higher or lower. So higher would be a positive answer if we're talking about the amount of rise out of the water. And let's see. So what we'll do is we'll incorporate that, the results of this formula there. So we need to say that we're going to substitute in our surface tension, which is 73 E minus 3, and we've got a cos of 0. Then we're going to divide by the density. Depending on which number you use, which numbers you use for water, you'll have different results here. So let's just be approximate for now, roughly 1,000 and 9.81, and then we'll say that R is half of the diameter, so 0.5 E minus 3. And we should have a capillary rise of around 2.97 centimeters. So that's the answer in meters. So a rise of about 3 centimeters. Next one, suppose that a fluid with a dynamic viscosity of 1e minus 3 kilograms per meter second and density of 1,000 kilograms per cubic meter flows inside a pipe with an internal radius of 10 centimeters and flow velocity profile versus distance from the center R of V is V naught times 1 minus R over big R. This is not a realistic velocity profile, but it's one that we're going to use to get an easy calculation for this this hypothetical question, where the max velocity is 1 meter per second. Determine the force per meter of pipe, so that would be length of pipe, that this flow places on the internal pipe wall. All right, so what we're going to need is our shear force formula. So the shear force from chapter 10 in our book is given by the dynamic viscosity times the gradient of the velocity as we move into the pipe. So this tells you the force that the fluid places on the wall of the pipe in the flow direction, and it has the same direction as the flow velocity does up here in this formula. Now in this case, the velocity is actually given by the symbol v, so maybe we'll write that in, or maybe we'll substitute in what the velocity formula was. So put that there. And we'll also need in the denominator to know what the direction into the pipe is. Well, if R is the distance from the center of the pipe, then R increases away from the center. And if we are at the wall, R would be decreasing away from the wall. So we're looking for negative dr. Okay, so we're going to differentiate this thing with respect to R and then take negative of that value. Differentiating so this constant just comes out. We can do that like this. And now taking the derivative of this stuff, this constant gets killed by the derivative. And then we are left with 1 over R. Okay, so that is the stress that we have on the wall. And we can convert that into a force. Where by multiplying by the area of the wall that we would be in contact with. So over 1 meter of pipe, that would be the circumference, 2 pi r, multiplied by the length. So maybe L is 1 meter. Okay, so mu v naught times 1 over r times 2 pi r times L, which means the r actually cancels. And we're left with 2 pi mu times v naught L. And the force per length, or force per meter, would be then 2 pi mu times v naught. All right, so mu is 1 e minus 3 kilogram per meter second. We don't actually need a calculator for this one. 2 pi times 1 e minus 3 kilogram per meter second. When you see it written like this, the meters times second is on the denominator. So that's a way to, this dash is a way to say that the seconds goes with the meters. It's multiplied by that. And where were we here? Oh, here we go. Then the other thing that we have is 1 meter per second. So meters cancels with meters, and we're going to have 2 pi kilograms per second. So that seems kind of strange, right? Second squared, actually. Kilograms per second squared. That's sort of weird. 2 pi e minus 3, I guess. Kilograms per second squared. 2 pi times 10 to the negative 3, or maybe 2e minus 3 pi. Kilograms per second squared. Again, a strange unit, but let's think. We wanted a force per distance, force per meter. So force is Newton, so this is newtons per meter is what we were looking for, and Newton is a kilogram meter per second squared. So, aha, you could rewrite this as a Newton per meter. Same thing. So there we go, 2e minus 3 pi newtons per meter, or approximately, you know, using 3.14, 6.28, let's say 6.3, e minus 3 newtons per meter. So it doesn't sound like very much force, and it's not. It's a very small amount of force that this flow rate with this kind of a velocity profile would be putting on a pipe over just 1 meter. Okay, final question. Suppose a flask, tapered walls, and a beaker, straight-walled, with the same base area are both filled with 250 milliliters of the same fluid. Will the base surface of the flask have a higher, lower, or the same hydrostatic force on it as the beaker? Okay, so because the flask has walls that are tapered in, if the base is the same size, then the flask must have the surface level to get to 250 meters at a larger height. You can sort of see the difference in this. These pictures are not quite to scale, despite having the same, it looking like it has the same base area like this. Look where the graduated cylinder marking is for the 50 on this one versus here. It's all the way up in the thing. So maybe to make it match, ignoring the tilt a bit, we might need to sort of stretch this more like that to really demonstrate just how much higher the surface of the flask would be because of that taper. So let's put that into words here. Because the flask is tapered in, the surface of the water will be higher for the same volume than in the beaker. This means the pressure hydrostatic pressure on the bottom surface of the flask will be larger. Because the pressure for hydrostatic pressure is equal to rho times g times the height or the depth that we've moved to from the surface. And so higher height means higher pressure, and the force, and therefore so will the force. Hydrostatic pressure on the bottom surface of the flask will be larger because the pressure is rho gh, and therefore so will the force also be larger. F is equal to P times the area. All right, thanks for watching.